if I were teaching this course live, I would go through within the class a worked out, relatively simple example problem from start to finish, because I believe related to setting up a combustion equation, because that's going to really be a large proportion of what you do in Chapter 13 is getting some familiarity with starting and writing accurately the combustion equation with excess air. And so that's what this module is all about, really, is just picking one example problem and trying to show you how to work through it from start to finish. It's a pretty simple fuel, but I think you'll get the idea, and you could, if you sort of master the techniques within this example, you're going to be able to analyze, I think, very well the combustion equation for any fuel described by C sub M, H sub N. And so here's the basic example problem I'd like to go through. It says a gas-fired boiler, familiar image that I've picked, uses methane, CH4, so that would be a model for natural gas, commonly used nowadays because of the economics associated with natural gas now. And it's using 10% excess air. And I would say 10% excess air for this particular steam generator, for this steam boiler, 10% excess air is very typical for this operating setup. And here's the problem statement. Determine the combustion reaction equation, the air to fuel ratio, and the equivalence ratio for this situation. This would be very common for you to do out in industry or in a commercial situation if you're testing for the heat content of fuels, all kind of applications associated with this. So let's plan your work. So there's the problem statement. I've simply replaced it. Let me move my picture. There we go. It says, okay, so here's what we'll do. So you're given your fuel, 10% excess air. You'll set up your stoichiometric equation. That's always going to be step one. Should be pretty easy, right? But you want to write it down. The next thing you do is you're going to determine the theoretical air to fuel ratio for the theoretical air situation. You say, well, I'm not asked to do that in the problem. Well, you're going to need to do that for the equivalence ratio value. So you might as well do that for the stoichiometric equation. Okay, and you check that off. So the next thing you're going to do is apply the 10% excess air factor. Remember, there was that factor 1.1 for 10% excess air. Or in other words, I could have worded it 110% theoretical air. It's very common. Different engineers use different jargon. Some engineers will say 10% excess air. Some engineers will say 110% theoretical air. It means exactly the same. Once you've got that equation, it's a simple matter to determine the actual air to fuel ratio. Remember, that's mass over mass. Mass of air divided by mass of fuel needed. And so you need that also for the equivalence ratio. And then you've got those two factors. And so determine the equivalence ratio and you're done. Report your work. Okay, well, let's get started. Let me move my picture again. So the theoretical air, wow, should be like child's play where you're going to write this down with pencil and paper where M is 1 and N is 4. CH4. M is 1, N is 4. I'm going to go through, and you can either go through and do the hard work of head scratching and figuring out what those things are, or just go ahead and recognize B is equal to M, C is equal to N over 2, and A is equal to M plus N over 4. And so A is 2. And so you can write down the red circle. Wow, you're 25% of the way there. CH4 plus 2 oxygens plus 3.76 times 2, or in other words, 7.52 nitrogens. And that results in 1 CO2, 2 H2Os, and 7.52 nitrogens. So I've labeled that 100% theoretical air. And in my work, it probably pays to kind of circle and label it 100% theoretical air or 0% excess air, whichever you prefer. Now, once we have that result, the air to fuel ratio is easy. How do I get so I'm looking with my eyes at my reaction equation, looking over on the reactants. What's the mass of CH4? It's just going to be 12 plus 4 times 1. Okay, 16. Okay, how about the mass of the air? It's going to be 2 times 16, or in other words, 2 times 32 plus 3.76 times 2 times 2 times 14. There you go. So 274.56 kilograms of air for each 16 kilograms of CH4. So the air to fuel ratio is simply 17.16 kilograms of air per kilogram of fuel. Now notice in my work, I haven't just said 17.16. I spell it out, and I've done this in my work life, right? Not just 17.16, it's 17.16 kilograms of air per kilogram of fuel. So air to fuel ratio is not purely dimensionless. Now we're moving on to 10% excess air. We're burning with 10% excess air. And so I'm simply going to plop into my stoichiometric equation the factor 1.10 for 10% excess air. And then I'm going to do the math. I'll do the algebra over here, right? And so I remember still got a CO2, I've got 2 H2Os, but I've got question mark amount of N2s. And if I show my work, all I have to do is multiply 7.52 by 1.1 to get 8.272. And then oxygen. What do I put for oxygen? Well, I just do the algebra. I just add up the oxygens over. I know I've got, let's see, 1.1 times 2 O2s, and then I've got to subtract off one of those and another one of those, and that gives me my leftover oxygens, 0.2. Okay, and so I did the algebra there, and that's, I've got the oxygen right there. And so it's as simple as that. Same idea, air to fuel ratio. I've still got 16 kilograms of CH4 from before. I do have to recalculate my air mass, right? Because I've got that 1.10 factor. Well, it's going to be 1.1 times the stoichiometric kilograms. It's going to be 302 kilograms. And so my air to fuel ratio is 18.88 kilograms of air per kilogram of fuel for 10% excess air. Wow. And now just go to the equivalence ratio. And I'm going to have to remind myself, what's the definition of equivalence ratio? Easy to forget. Go back to my book. It's the fuel to air ratio, actual, that's with the 10% excess air, divided by the fuel to air ratio stoichiometric. Well, remember, I just got done calculating air to fuel ratio, not fuel to air. So I'll have to be sure that I get that straightened out. So with pencil and paper, I'm going to kind of make up a little table. Here's my 10% excess air part. Here's my stoichiometric air part. I wrote down my result, air to fuel ratio 18.88. I'll take the reciprocal of that to get fuel to air, 0.052997. Stoichiometric side, same idea, reciprocal of 17.16 to get 0.058275. And a ratio of both of those, just by the definition of equivalent ratio, to get 0.909. Okay, great. There's my answer. And what's my practical conclusion is I'm running a lean mixture in my boiler. That's what I want for steady state, steady flow, open system. I definitely want to run a lean mixture for safety and to get my money's worth. I want to burn all the fuel I'm buying. because the little meter is clicking outside the building as you're buying your CH4 from the utility company. And that's the example problem. So do you see how quickly that went? As long as you work through the combustion analysis step by step, don't take any shortcuts, and show your work. I will tell you that as an undergraduate, my biggest downfall in this area was not showing my work. I tried to take shortcuts because I was lazy in my writing. It just seemed like it was such a chore to write things down. But as I went along and got into graduate school, and then certainly in my work life, I saw that it wasn't quite the chore that I thought it was as an undergraduate, because I end up having to rework so much. So it should work down the page, show your work, and this really becomes really pretty easy. So I hope that helps you plan your own work as you have your homework problems in Chapter 13 and you're looking ahead towards finishing up this class.